Hello everyone, and welcome to the Unit 2 Test Study Guide Guided Notes. I am going to start on number 15. If the quadratic parent function is reflected in the y-axis and vertically compressed by a factor of 1/2, write an equation to represent the new function. Our new function, f of x, is going to be reflected in the y-axis. It's a quadratic, so the y-axis is the negative. The quadratic here, of course, is the squared, and then it's going to be vertically compressed by a factor of 1/2. In 19, describe all the transformations from the parent function given the function below. All right, well, the first thing is here inside the parentheses, I'm going to do a horizontal stretch by 1/2. I'm going to reflect it because of the negative over the x-axis. I'm going to vertically stretch it by a factor of 3. And then I'm going to move it up 7 units. The next is looking at number 23, and I'm asking you to graph the cube root function, the parent function being the cube root of x, and that looks like 0, 0, 1, 1, -1, -1. Those points come from plugging in -1, 0, and +1 into the graph. So there's the parent function. Now, all we're going to do with this function is move it to the left 4 and up 3. That means the new vertex goes from 0, 0 to -4, 3. And then I'm going to vertically stretch it by a factor of 2. So that the point -4, 3, then next points look like this, and the new function itself does something like this. Okay, the domain for this new function, which I'll just highlight, I guess, in green here, looks like this. It's not super easy to see, but there it is. The domain for this function is all real numbers. The range for this function is all real numbers. The x-intercept, I can find that by setting the function equal to 0 and solving for x, or I can use the calculator, and let's see. I can use the calculator and type in my equation. So that's going to be math option 4, and oops, it's got to be in y equals. Let's clear that. So y equals 2 times math option 4, the cube root of, I believe that was x plus 4, close parentheses, and then plus 3. Let's take a look at the graph of that, and there it is. Our scale is different, maybe different than what you see on your calculator and different than what we're graphing on paper, but the point of this was to be able to look at it and say, okay, I can identify where that x-intercept is. I can move the cursor along to where I think the 0 is, and I can get awfully close to that value. You see the y value is getting closer and closer to 0. So let's go second, calculate, and let's find the 0.
Calculator error makes
Never
solving
mind.
math problems
I don't even know
effortless.
how
With
this
photo
works.
problem
Sorry about that. We'll close the calculator. What we end up with after we do second calc intersect, that's what happens when you find the cheapo, is the x-intercept, I believe, is at something like -7.35, 0, and then the y-intercept is where x equals 0, and that occurs at, I can't remember what that is. I think it's 0,6.71, but double check these on your own calculator. All right, the extrema. Are there any extrema? We didn't really talk about this, but I mean any high or low points. And the answer here is that there are none. This function is increasing over the interval of all real numbers. You could also say from -infinity to +infinity. And it is decreasing nowhere. It has no or none, no, not decreasing anywhere. The end behavior is that as x approaches -infinity, the function approaches negative infinity, and as x approaches positive infinity, f of x approaches positive infinity. So as the x values get more negative, the function gets more negative. As the x values get increasingly positive, the function gets increasingly positive. Okay, moving down now away from transformations and talking about graphing piecewise functions. This is one function that's broken up into three pieces. The graph of negative 3/2 x minus 6 is the first piece. It's a line. It happens to have a x-intercept of negative 4, I believe, with an open circle. And I know that by when I plug 0, when I set this function equal to 0 to find whoopsies. What I mean is that when I plug in 0 for x, which would be this point right here where the circle is, I get negative 4. And so that's how I know where the x-intercept is. And then I'm counting the slope. 3, 2, 3 over 2. And the graph of this piece looks like that. Next one, I'm looking at the absolute value function from negative 4 to 1. So from negative 4, I can just plug in values for this. There's partly, the absolute value of x flipped over the y-axis, flipped over the x-axis. And then lastly, I'm looking at the square root function, which again is going to look something like this. It's half of a parabola turned on its side. With a vertex at 1, 3. Let's move to the right 1 and up 3 from the origin, so over 1 and up 3. And then this function, when you plug in these values, follows a pattern like this. We have to make sure that we pay attention to where the circles are open or closed. Whoops. And so it will be open right there and closed here. All right. The domain for this function is all real numbers because it continues to the left and the right, and any open circles are filled in here by these closed circles. The range of this function is from the low point, negative 4 included, up to infinity because both the line and the square root function continue to get increasingly positive. There are discontinuities that are jump discontinuities where x equals negative 4 and x equals positive 1. In number 30 here, I'm talking about even, odd, and origin symmetry. Even and odd functions, and odd functions that have y-axis, x-axis, and origin symmetry. So you can look at this visually and see that it has y-axis symmetry, it has x-axis symmetry, and it's a little harder to see, but it does also have symmetry with respect to the origin. And we can test this out algebraically. So we said it has y-axis, x-axis, and odd, and that it has origin symmetry. So to see if it's symmetric with respect to the y-axis, I'm going to plug in negative x values. That means that when I plug in positive f of x, I get the same thing as when I plug in negative f of x. So when I plug in x squared minus negative y squared equals 4, do I come out with my original equation? And that's x squared minus positive y squared, yes, equals 4. So check, it has y-axis symmetry. Now to check if it has x-axis symmetry, I'm going to say, okay, are f of x the same thing as f of negative x? In other words, when I plug in, nope, that's not right. Sorry, that was just y-axis symmetry. Okay, when I talk about x-axis symmetry, it is, do I get the same thing when I plug in, do I get f of x equal to negative f of x? So when I plug in negatives for the, I did this last one backwards, I'm sorry. This demonstration was for x-axis symmetry when, I just didn't even do it right. I'm sorry, I'm going to redo this one. Let's start all over here with 30. Okay, I did the algebra and the explanation backwards. If something has y-axis symmetry, what that means is that when you reflect it over this line, both the positive x values and the negative x values are going to give you the same result. And so what I'm doing with this is saying, okay, if I plug in negative x's, do I get the same thing as the original equation? And yes, x squared minus y squared equals 4. So this has y-axis symmetry. Okay, now for x-axis symmetry, that's if I reflect it over the x-axis. Do I get the same thing, f of x? Does f of x equal negative f of x? Well, if I take positive x values and then I take negative y values, do I get the same thing? I do. I get x squared minus y squared equals 4, which is my original. Now, when it comes to origin symmetry, that is, does f of negative x give me the same thing as negative f of negative x? And so, oops, let's see, does f of x give me the same thing as negative f of negative x? Well, when I plug in negative x values, do I get the same thing as when I plug in negative y values? And I do, in fact, get x squared minus y squared equals 4. So this function has y-axis, x-axis, and origin symmetry. Okay, moving on to number 39. What I'd like you to do here is a composition of functions. It's not multiplication. So you are taking the values for the h function, which are 3x, which is 3x minus 1, and plugging it in everywhere you see x in the f function. So that's squared minus 2 times you see x, you write 3x minus 1, that's the h function. And then you get negative 9x squared minus 6x plus 1 minus 6x plus 2. For the sake of time, I'm not going to simplify that any further, but you would get that down into simplest form by combining like terms. In 45, I'm asking if this is a one-to-one function. That's asking, does it pass the horizontal line test? That means, can I draw a horizontal line anywhere through this function and have it only touch once? If the answer is yes, it passes the horizontal line test. It means that it's a function. It means that its inverse is also a function. Which means, of course, if it's a function, it passes the vertical line test. If it passes the horizontal line test, it means its inverse is also a function. Last one here. I'm going to see if it has an inverse and then find it. Well, I take y equals the cube root of x minus 7 plus 2. The first thing I do is switch x and y. It's the cube root of y minus 7 plus 2, and then I solve for the new y value. That's cube root. I'm going to cube both sides. So I get x minus 2 cubed equals this, equals y minus 7. And so our new inverse function is x minus 2 cubed plus 7. Okay, that's it for the Unit 2 study guide review.